neutralize it, make the charge zero, because charges are not favored thermodynamically in a nonpolar solvent. The interior of that membrane is the same as benzene, a nonpolar solvent. So, I don't know how this came about, but the point is, the proton has a safe ride. It can't come off, because if it could come off, then that energy would be wasted. So the only way it can hop off the merry-go-round is when it goes over to the exit port. Out it goes. So here is a top view looking down onto the orange slices. Remember the top part of the ATP synthase? This green arrow here is, imagine that's the tip of the gamma subunit. As this thing rotates, it's not just the tip, it's the whole thing here that's hitting parts of these dimers. Okay? But notice here, like this diagram, I don't hate every diagram in Leninger, okay? Well, it seems that way. But notice how they've drawn it here. They're trying to indicate, like this guy right here, here's one dimer, and so they've drawn it with these straight edges to indicate it has one conformation. Then we've got this kind of loop-the-loop thing to say, hey, this dimer is in a different conformation. And lastly, this one here, a little bit different than this one. But the point is, these guys are in 3 different conformations. Okay. So, what we can see is that this dimer here is empty. It just lost its ATP. This guy here has formed ATP. Okay, what do I don't like about this? The formation of ATP should be right here at the interface between the alpha and the beta subunit. This looks like it's only on the beta subunit. That's not true. But lastly, over here, this is when ADP and inorganic phosphate, again, it should be right at the interface, had just come into the binding site. Cool? So, the 3 segments of the orange slice are in different conformations. Why? Because this one here just got kicked in the pants by the gamma subunit. And that's why it's releasing the ATP. And then it takes 3 protons from the positive side going through the wheel. So again, we've got, in yeast, we've got 10 binding sites. The 3 protons coming out are not the same as the 3 protons coming on. It's a continuous wheel. But the energy from 3 protons is enough to make this thing change from here now to up here. So it's rotating counterclockwise in this diagram. I just kicked you in the pants, and that's why you're releasing the ATP, etc. So it always takes 3 protons, the energy of 3 protons going through this wheel. In reality, it's a continuous flow to create 1 ATP. So here's the last beautiful thought for today, because I've downloaded a lot of information to you, okay? I want you to go back, I want to focus right here. When the ADP and inorganic phosphate come in. A long time ago, it seems like ages ago, we were talking about enzyme active sites. This is an enzyme active site. There's 3 of them. Enzyme active sites, according to Pauling, Professor Pauling, 2 Nobel Prizes, remember? More than you and me. Pauling suggested that enzymes best bind to the transition state. Not to S, not to P, but to those hypothetical things which does occur halfway in between. So that means the enzyme always, in any enzyme catalyzed reaction, always forms the most weak bonds to the transition state. That's why it lowers the energy and makes the reaction go faster. Well, what does that have to do with this? Well, it turns out in measurements of how well this dimer binds the transition state, this thing, apparently, each one of these active sites, they're identical. Each one of those active sites makes so many weak bonds that it lowers the transition state energy. Remember we had free energy G on the y-axis, reaction coordinate on the x-axis. So we had this hump for a non-enzyme catalyzed reaction, and then a smaller hump for an enzyme. This thing makes so many weak bonds that it lowers the transition state energy to almost zero. So that's very interesting. It says that this mechanism requires virtually no energy to make ATP. You can make ATP without putting in hardly any energy. But you don't get something for free. So instead, you need the energy to rotate the crooked finger to break all those weak bonds so it releases the product. And that is super cool. So this is like, each one of these enzyme active sites is like the ultimate enzyme. It lowers the energy so much, it makes the production of ATP easy. But it won't release it unless it gets a kick in the can. Have a nice weekend. See you on Monday.